Welcome, everyone, and thank you for joining us today at HSE University's Master of Data Science degree program's industry webinar. Today, our speaker is Fedor Ratnikov, and the topic is how machine learning helps in studying the universe. Before we start the presentation, I would like to mention a few formal moments. First of all, the recording of this webinar will be available in a few days. During the presentation, if you have any questions, please post them in the Q&A feature. There is also a chat, but it will be easier for us to track all your questions in Q&A box. And after the presentation, we will have the special section for Q&A. So please feel free to post your questions. Okay, I think that we can start. Fedor?
Okay. Well, thank you for introduction. And well, I hope this presentation will be kind of entertaining. So the idea, so I try to explain you to describe how we study the universe and how do we apply the machine learning approaches for that. And probably about myself, I have a physics education. So I'm a physicist since, well, essentially the entire career. And now for about 5 years, I moved a bit into machine learning stuff. And now I work in the High School of Economics on the faculty of computing science. And the idea of our current efforts is to apply the modern machine learning approaches to the fundamental science, and particularly to those about studying the universe. So, so I built my presentation in, well, essentially in 3 topics. So the first big topic is some discussion about the physics. Essentially, what's the primary purpose of our studies? Then there will be a very quick discussion of machine learning per se, because I suppose that people here are interesting in computer science, and so they're aware of machine learning as a basic science. And then we try to merge so how that machine learning does help does solve those problems that we have in our physics stuff. So let's go for physics. Let's start from the basics. So we have the universe, and the universe does so everything around us have some particular scales, and so you may ask yourself what is different. So we have many different natural science, physics, chemistry, biology, also the human science, etc. So what is different between those sciences? And the answer from my perspective is that they study our universe on different scales at different sizes. And so for example, as you know, the chemistry studies the interaction between the interaction of molecules, how they're collected, how they're built, and those properties. Then, so on the higher level there is a mechanics, right? On the low level there is atomic physics, etc. And what is interesting is that that physics as a science covers the biggest scale of the biggest ranges of scales. And what's what's also interesting that physics covers the biggest scales, starting well, say from dimension of Earth, the solar system, etc., and up to where we can get. So essentially up to everything about visible universe. And also the physics covers the smallest sizes, the smallest scale. So starting below the chemistry, so we have the atomic physics, then we have, so as you know, the atom is made of smaller particles, which is, well, atomic nuclear, proton, neutrons, and reactions around, and then protons and neutrons are made again from smaller particles, which are called quarks, and so on. So essentially, physics covers the biggest and the smallest scales, and the paradox is that those extremely large scales and extremely small scales are connected very closely, and I will discuss it a bit later. What's important right now is that when we're studying universe, we study different scales of objects, and essentially the biggest scale. Okay, so now we want to study universe. What we know about universe? We're pretty confident that our universe appears as a result of Big Bang, and it happens about 13 billion years ago. And soon after the Big Bang, so in the very beginning, universe was small and very hot. So at the early stage, it was a very hot bouillon of energy, I would say. And then it starts expanding, and so at some point, some elementary particles appears. Then those at further expansion, universe becomes colder and colder. So then those particles, for example, quarks, were combined into protons and neutrons. Then later, those basic particles were combined together, so they form the nucleus. Those nucleus are interacting, so they build the more heavy nucleus, and they form at some point the structure. Some structures have formed in the universe. And well, after those 13.8 billion years, we are at the current point where we have that universe with all stars, galaxies, etc. So this history is this history and those processes are modeled and studied and are studied by the physicists. And the funny thing is that we understand pretty well right now what's happened, what's going on, approximately from the stage of when the elementary particles appeared till our days. So essentially, physicists understand pretty well everything that happened beyond 10 to the minus 4 seconds of universe life. So you can imagine. So what we want, what we still do not understand exactly, and for the donut model exactly, those events which happened between, say, 10 to the minus 10 and 10 to the minus 5 seconds. So just imagine which point in the universe life we are studying, how teeny that region is. However, that region drives the current state of our of the universe. Okay, so now so I said that we understand pretty well what happened to, since that 10 to the minus about 10 to the minus 5 seconds and now. Does it mean that we know that we mostly understand our universe? And I must say that no, there are big puzzles, and so there are big questions which we still do not know. We probably do not care about that when we live on the Earth because it doesn't affect us directly. However, there are serious questions, and I'd like to discuss two of them. So one of them is the question of material and material and anti-material distribution in the universe. So you likely know what the antimatter is. So probably you know when object and anti-objects are collided, so they disappeared with just flash of light, flash of energy, etc. So essentially, the matter, the matter is the laws of physics, laws of matter, are symmetric with respect to the matter and antimatter. So, and as soon as well, from another side, we know that we all are made from matter, and our planet is made of matter. The solar system is made of matter, and actually the close galaxies are made from matter. But once the universe appeared from the Big Bang, we naively should expect that the contribution of matter and antimatter in the universe is more or less equal, because originally there is no bias in that direction. Well, however, we observe no antimatter in the vicinity in our galaxy, but probably there could be some other galaxies that are made from antimatter, etc. Yeah. The interesting thing is that it's not the case either, because even if we imagine that there are some regions of universe which are made from matter and another region which is made from antimatter, they should touch each other, and then there must be some radiation from the annihilation of matter and antimatter. And so this radiation is pretty well defined, because, well, so essentially they are either protons or electrons which annihilate, and so it must be a very, very clear radiation signal, but we do not observe. So essentially, we may conclude that the contribution of antimatter in our universe is very teeny, and it is a very big question mark. Why is that? Another question, and, well, I would say puzzle for our universe, and, well, essentially for the world around us, is the presence of dark matter. Then, so there are galaxies, we observe them, And so some of them are rotating, and you can imagine that the rotation of galaxies is driven by the mass distribution inside of it. So when we see the galaxy, we observe we, we observe the visible matter, and then we can calculate what is the expected rotation speed. And we figure out that that rotation speed is very different. The actually measured rotation speed is very different from that which we would expect from that distribution of the visible matter. And and now, if we still have that map for the rotation speed, we can estimate the mass distribution which would drive, which would make that rotation behave like what we observe. And this is that analysis. The example of that analysis for one of the galaxies is presented on the on this right top plot. So we see that the distribution that the mass distribution around the center of the galaxy is much bigger than what we observe. And by the way, what
I'm so sorry, Fedor.
Yes.
I'm so sorry. I think that we can't see your slides. Have you a presentation?
Say it again. You can see it.
Yes. I just noticed that there are no slides. Could you please share your screen?
Just a second. Where is it? Hold on.
Perfect. Thank you.
But I try to play this. Oh, okay. So I hope So is it still there? Is it still there?
Yes. So now we can see the slides.
Yeah.
Thank you.
Okay. Sorry. Yeah. Okay. So the question was, the last point I was asked, what is the visible matter? Well, the visible means that we can observe it, and if we can observe it means that, but if we can observe it visually, it means that it interacts with photons. So some photon can so this material can reflect or emit photons. So it means that dark matter, which is the extra for that consideration, is a kind of material which has gravity, which drives essentially the rotation, but it does not interact with photons and any other normal particles. So usual particles. So it must be some very special domain of particles of matter, which with respect to our regular matter. The biggest puzzle is that essentially we need 5 times more matter in the universe to explain the observed dynamics of objects. So this means that about 85% of our universe is done of something that does not interact with our regular visible matter. And the question mark is, what is that 85%? And you can imagine. So we essentially do not know about. We know almost nothing about about physics, about nature of 85% of our universe. So it's like you live in your apartment, and at some point you figure out that your heating bill is 5 times more than you expect for this footage, right? Okay. So how can we study that problems? And now we come to that interesting point that so that how now so now I'll try to explain how that super big and super small scales how the physics of universe and physics of elementary particles are related. So as you see, so here I zoomed that region, so you see, and this so one of those is that time since the Big Bang corresponding to that state, and another important point is the energy. So it is the average energy of the universe at that point, and you see that this point, so that the closer to the beginning of the universe, the bigger corresponding energies of the particle of those universe, and as a result, it is the bigger energy or mass of particles which can live, which can sustain at that stage of time. So the colder universe became so essentially the particles became colder and colder. So with smaller energy, only those low mass particles survive. Those particles which cannot decay to other particles. So this essentially make a connection between that extra big. So when we want to study universe at very early state, essentially we want to study the behaviors of particles at that high energies. And by the way, so this energy, so 100 GeV, you probably so it's giga electron volt, and you probably remembered well anyway. So the mass of proton is about 1 GeV. So it's the energy of the order of the 100 masses of the proton. Okay. So this makes that bridge between study of universe and study of elementary particle physics. So now I switch to the microverse and to the microverse and discuss a bit what we know about the elementaries, the smallest particle, elementary particle. So the physics of the smallest particles, the elementary particles, is described by the model which is called the standard model. So essentially, it is very elegant model which consists of 17 particles, basic particles, which are all drawn presented here in this table. So those particles are quarks. Quarks are those particles of which, for example, proton and neutron are made. So proton is done of two so-called U quarks and 1D. Neutron is done from 2D and U quarks. Well, so then there are leptons. Leptons include the very well known for you electron. This is the important component of every atom. And then there are also harder partners, more heavy partners of the electrons. So they're called, so there are three generations, so they're called the muons and tau leptons. Okay, and so then there are four particles which drives the interaction. So as you probably know, the interaction between particles, for example, the electromagnetic interaction is driven by the particular particle. So when two objects interacts, it could be described as an electromagnetic field which interacts, or it could be described as an exchange of particles. So there are just four particles, four types of particles. So one is the photon that you know pretty well, and this particle is responsible for electromagnetic interaction, all of that stuff. Then there is a gluon. Gluon is the particle which connected to quarks, and essentially it is responsible for keeping for having quarks in for forming the nuclear of the atom. Well, and then there are more. So those two particles are massless. And then there are Z and W bosons. So there are two heavy particles which are responsible for weak interaction. Well, you probably know the weak interaction is responsible for beta decay. By the way, weak interaction is the primary component of the reaction, nuclear reaction in the solar. So it is the primary interaction which provides the heat for our life. Well, and then there is a very interesting particle that is called Higgs boson, which essentially responsible for masses of all other particles. And Higgs particle it was a component of the Standard Model. Standard Model is pretty old. It was developed, well, I would say 50 years ago. But the Higgs boson was actually discovered only in 2012. And this essentially was the third big problem, big puzzle of the physics. So the question how the mass of all the objects is produced, and so this puzzle was answered in 2012 by experiment on the Big Hadron, by the experiment on the Large Hadron Collider, which I'll discuss a bit later. Okay, so essentially to study the universe at early state, we want to study details of the standard model and details of the interaction between those particles. So we have a base understanding for that model, but we have to tune it to understand the details of interaction, and particularly these details drives the history of the universe. Okay, by the way, this is another view on elementary particles, as they are pretty teeny, so they're much smaller than the nucleus, so you can imagine them as you want. So they have the pretty arbitrary names and images. Okay, so how can we study what things are made of? So we know that things are made from small parts, which are made of smaller parts, etc., etc., etc. Is it infinite loop? Apparently not. So at some point we come to those parts which may not be destructing anymore. So they do not contain smaller parts. Is the end of the story? Not quite. we still still can go further and just smash those particles, those objects. What should we get? So if suppose we smash two bears, we should get something like a gem, right? The interesting thing is that for for the collisions of elementary particles, it happens in very different way. So in contrast to barrier, when we get some smash from them, as a result of particle collisions, we produce a new particles. So as a matter of fact, those new particles are not the constituents of the original particle. So they're really new objects. And those objects may be very different from those that are colliding. And particularly, as a result of that smash, we can create those particles which do not exist in the universe right now because they are too heavy particles. But they did exist in the very beginning of the universe, at that point which we are going to study. Okay. So that's the way how we get to that, how we're trying to get to that point of the universe. Well, so just to remind you, we are talking about this region of the timeline. Okay, so now how we can produce those particles? As I explained, we may try to smash those particles we have in hands, and those convenient particles we have in hands for smashing are protons. Protons are made of quarks, but those quarks are confined in the proton, and as a result of that, that condition, we produce a lot of more small particles. Essentially, this is we still follow that Einstein famous Einstein formula that energy is related with the mass, but usually we know it in directions that if we have two particles which are annihilated, then we extract the energy. Then we extract energy. But the opposite is also valid. So if we concentrate energy at some point, it could produce a new particle, so new material. And now, if we want to study those, we do not need, colliding particles is not enough because okay, so they are collided, we get new, and what? We have to be able to study the result. And for that, we need to somehow to put a detector to detect what happened in that collision. So we have to make some kind of camera for that. Okay. So I have to go fast. So let me just go to the slide. So this is a small movie about this installation, which is called the Large Hadron Collider at CERN. So it is located near the Geneva, on the border between Switzerland and France, and this is a huge tunnel and in the tunnel those protons are accelerated protons are rotated in two directions. So essentially they are rotated at pretty huge speed, so very close to the speed of light. And so there are 4 detectors there. So there are 4 points where those protons are colliding. And so what's happened? So there is such a point, and there is a huge installation, which is a detector. So now protons are colliding, new particles are produced, and there is a detector which can say which can store the results, which can store the results of those collisions. So that's great. The problem is that that to get enough data, those collisions are made 20 million times per second, and those detectors operate several years ago. So as a result, we have 100 petabytes of data. How to process those data? All days, their process it was a straightforward. So we get those results from camera, and then film was processed, and pictures are manually analyzed by experts like on this slide. So and then they reconstruct the picture into particular decay. So this is the famous picture for discovery of the omega minus hyperon in 1957. Nowadays, there are much bigger collision with much higher energy, so events look like this. So something like this is detected every at a rate for 40 million per second for several days. What should we do with those events at LHC? Okay, so this is an example of scientific paper. Okay, let's go to the next part. So this is a short part because I suppose you are aware of machine learning. I apologize. I had to make that huge introduction just to give you an idea what we are working with. Okay. Well, machine learning now is everywhere, so there is a huge success, and it is used in very different areas for decision making, for simulations, for automatic car driving. Well, it's run. So here I'd like to discuss a little bit the principal difference between those data models which are used in natural science and those models which are used by machine learning. And let's start with natural science. So let's discuss what the scientific model is. So for scientific model, the main paradigm is that model predicts data. So essentially, there is a loop. So model is the primary, the primary for the study loop. So there is a model, then we have some predictable observations, and we check those observations. So we have a data, and so model can predict data, and then as far as predicted that observed data are consistent with prediction, we may judge if model is good or not. So the principle specific of those models, of those scientific models, particularly physics model, is that as a priori, those models are a priori driven by some fundamental laws. So, for example, if we consider some weight where dropping from some height, then we should expect that the height to be quadratically dependent from the time which is used by the DAO. Well, so for the scientific model, usually have a minimalistic number of parameters or degree of freedom, and this is driven by the Occam-Razor principle. So such a model may be easily extrapolated beyond the domain where has been tested. So particularly if we study the Newton law, well, on the Earth or on this solar system, we may assume that it does work in other systems as well, and even in higher scales. And what's also important is that we can pretty well interpret our predictions. However, there are problems with that scientific model. That what to do if our model is not good, doesn't describe data. And for example, if we make that test with dropping weight, and but there is a air resistance, so we do not have that quadratic law, and we are dead in the water. Here is a particular example of this. Of that model. It is our standard model, and for example, that observation of the Higgs boson. So there. Well, so the machine learning model is very different. So it is a descriptive model, and the paradigm is opposite. So now the model describes data. So data is primary, and model is built on top of that to describe those data. So we have no essential a priori assumption about dependence of parameters. Such models is universal, so as there is no assumption. But the price for that is the huge number of model parameters, which are very hardly interpretable. And we should always remember that such a descriptive, the machine learning models, may not be reliably extrapolated to a new domain. So the example of well, actually, it's not machine learning, just a data learning model is an archery. So it is a very complicated interaction of gravity, aerodynamics, tension, oscillation, and so it's very hard to get a model of the biodynamic. Well, however, does it mean that the good archer should be a good scientist or analyst to solve all that relations? Absolutely not. So it is very possible to consistently hit a target without all that studies, just by experience. Okay, so here is a list of typical machine learning problems we solve. So that supervised learning, where we have a very well-defined label samples, and there is unsupervised learning, where we only give a hint what we'd like to obtain. Then there is a reinforced learning, where we give a system just a hint what could be good or bad in particular situation. Then there are feature learning, well, and anomaly detection, which learns some, which tries to find some outliers in data distributions. So there are different kind of machine learning models. Now let's get to the topic of this presentation. So how machine learning helps us with study. The typical processing for the LHC experiment consists of different parts. So data first are selected by hardware or software trigger, which select only interesting result from those 40 million events per second. We cannot process that many events, so we essentially have to suppress rate by factor of 4. And so this is done by the trigger. So then once events are available, we have to reconstruct objects and analyze and get a physics result. And here is a map where machine learning actively works in these tasks. Uh, I'd like to start with RoboShifter. It is a very interesting approach. So which helps human to which takes the data taking operator. So essentially, when detector is running, it is pretty complicated system. So it's often so the quality of collecting data must be monitored pretty closely, and so we can give that information about data uh, to machine learning system, which educates itself. So essentially, it has a previous information about which data are supposed were selected as good or bad, and then try to predict the idea about a new data. So essentially, it helps human to make that analysis. So this is another recommendation system, which is based on the supervised learning. Well, essentially, it's supervised learning in this case. So another stuff is the reconstruction. So here is so detector is a complicated part and complicated system, and it consists of different subdetectors which collects different information about the particles to be able to produce to produce the information. So as a matter of fact, from those signals from different signals of the detector, we get an information about particular event, and this particular event derives our so this is an essence of our physics analysis. So namely here, this red point could be that particle which properties we are trying to study. So converting this result to the parameter of the particles, which is kinematics, or even just the particle types. What's this type of the particle is a pretty complicated task which analyze simultaneously a huge amount of information. And so this part is more and more actively use different machine learning approaches, starting with simple supervised one, two, and up to the unsupervised clusterization and all that stuff. Well, then and another very important part is the inference. So suppose we have some response and we want to extract the model parameters. So this is the ultimate part of our study, to get information about model, about our model, which describes the matters, so that essentially is projected to the universe. So how to extract the model parameters? The normal case, well, it's maximum likelihood. So we have a parameters, and then we have a response, and we try to fit trying to find the set of parameters which optimizes the probability of that observation. However, it is very complicated in the system, because the system is very complicated, and as a result, the inference is done by the solving the reverse problem. So essentially, we're trying to change parameters, and then we simulate the system, and we extract what the result we expect to get to obtain, and compare that results with actual observation. And for that, we need a huge amount of simulation data, because it's, well, essentially it is an iteration procedure. And for this part of simulation, this simulation is very expensive. So actually, the most of computing resources used by the high energy physics are taken by the simulation. So nowadays we are trying to build generative models which are trained on the actual slow simulation, to get a fast simulation which would provide us with ability to solve that to solve that inference problem in reasonable number. So here is a just primary, most important areas of machine learning applications which are used in experimental physics. So this reconstruction we discussed. Then I didn't discuss, but this real-time event selection. So that's necessary to suppress it about four orders of magnitude stuff. Then generation particles, and also the search for very rare events. So those are actually those events which are interesting for us are very rare. Very rare means about one event per several billions of not interesting events. So it is a very selective system. And this is where the artificial intelligence, machine learning, or regression, you may call it how you want, come to the and this is essentially this brings me to the conclusion that actually I'm very excited with that stuff we are doing right now, and how we essentially merge the computer science and physics. So it is it's very advanced physics merged with very advanced computer science. For this type of activity, a lot of data are necessary to answer our question, and data needs to be collected, filtered, reconstructed, analyzed, and those computing science approach, data science approaches are actively used for this. And in our area, particularly in our group works in those experiments at CERN. So we work together with other physicists, and the group essentially consists of physicists and computer science experts. So machine learning experts work together with physicists to build that very powerful data processing system. And those, as a result, that brings us to investigation and apparently to solution for those very strange puzzle that's set in our universe. So I suppose you are the young people who looking forward for putting yourself into some track, and so particularly this is a very interesting direction to join the exciting efforts from either computing science or physics side. Thank you. So now essentially I would be, if you have any questions, I would be happy to answer any question from fundamentals to practical questions.
Actually, there are questions on Q&A. For example, what programming languages are preferred to machine learning and LHC? I'm sorry.
Well, so you may know that the machine learning is usually made in Python, and however the most software of the LHC is made on C++. So this makes a little bit problem, but probably you know that the Python for machine learning is essentially the wrapper, and inside it's usually the stuff which relies on GPU. So it's essentially a search bar.
Any example of such dynamics that are not explained by visible matter? It was the question 20 minutes ago, maybe we got it there.
Well, I thought it was exactly that plot that the picture that I showed. So this one. So the top picture. So how it works? So if you have if you know the material distribution, then then you know the essentially the gravitational field around this cluster. So if there is a if there is an object which is rotating around, it rotates with very well defined speed. So like the the speed of satellites around the Earth are driven by the mass of the Earth, and they essentially and it doesn't depend on the mass of the satellite itself. Yeah, so we can calculate those speeds, those rotation speed as a function of distance from the center of the galaxy here. Using the if it is based on the mass distribution of the visible material distribution. This is a red line. So essentially, it means that the mass is concentrated closer to the center, and far from that rotation speed is decreasing. Yeah. However, if we we may solve the reverse problem. So we know the map of rotations and then extract what is the mass distribution. Yeah, and this is the white curve. So it's essentially we evaluate the mass distribution basing on the rotation speeds, and this difference is exactly that visible effect of the dark matter existence. So,
oops, I'm so sorry. Yeah, thank you. There are also questions. For example, where is all this research published? I understand the data is gigantic, sorry, but is any of the data maybe something associated with published work is public?
Well, so this very good question, by the way. So the question of publicity of those collected data, and particularly probably you know that astrophysics data are all public. For the high energy physics, data were not public until recently. Until recently means, well, 10 years ago, all data were private and never released to the public. Now it is changed, and as a matter of fact, there is more and more data are being open to the public. The problem here is that which kind of data we want to publish, because if we publish the raw data, just readout of the detector, it is just a bunch of numbers which so one needs a lot of knowledge and a lot of expertise converted into something reasonable. So I flashed that slide of for the publication, for the scientific publication, but probably you noticed that there are about 2,500 authors of the scientific paper. So that many people are doing that experiment. So as a matter of fact, usually even me as a collaborator in the experiment, I'm not aware how data are organized for the particular subdetector. The subdetector experts doing this. So it makes a very little sense to publish this data. So what we are trying to do we still try to work on reconstruction of those data. So some kind of physics objects, basic physics objects are reconstructed, and then we publish this data for the external analysis. So that's how how we do it well nowadays.
Thank you. Is there any basic course as an introductory to learn ML for physics? And another question, is a physics degree a prerequisite for doing ML and LHC?
Well, I believe there is a course in Coursera that's well either Yandex or HSE based course. I just know my colleagues who prepared and care of that course, which is dedicated to particularly to implementing machine learning for LHC experiments.
Mm-hmm. In what are other areas of physics is ML is majority used presently? Do you expect to see new applications of ML? If yes, what would they be?
Say it again. I didn't quite good.
I'm not sure that. So, in what are the areas of physics is ML is majority or used presently? Do you expect to see new applications of ML? If yes, what would they be?
Okay. Let me answer it in the following way. So actually, this effort of applying machine learning to the high energy physics, to the accelerator physics, is highly supported by Yandex, and the reason for that is that it's essentially it is an attempt to apply machine learning to natural science, assuming that high energy physics is probably the most challenging, the most complicated area of the natural science. And what is specific for, so what is specific here? We figure out that we cannot just take machine learning, the approaches which are developed for industry and just put it into the science. The reason is that they are very different purposes, very different targets, very different metrics. So, for example, just as a simple example, suppose we want to. So now it's a lot of hype around generative models, and when we want to generate, well, say, cat images, then it's important that, so what's the quality metrics? That cats look like cats, so it is essentially the visibility. And if we speak from the perspective of distributions, then so the feasibility means that our generated distribution is in body close to those to original distribution. So essentially you do not care if a cat has. So it's important that cat has true ears and true eyes, but we do know that. But the length of the but the length of the tail is not that important. For the science, those tails of the distributions are sometimes more important than the body of the distribution. So essentially, those studies are, as we study some very rare effects, very rare events. So we are very dependent from the tails, and so we have to develop a way to train generative models so they would take care about those tails we are particularly cared of. So this this still generative models from machine learning perspective, but they're different. But we need to develop a different approach for that. And actually there are two ways for that. So either we come to machine learning experts, high-level experts, and say, okay, we need that problem to be solved. or we learn our, so we take our own machine learning experts to develop that stuff, well, say from the CERN stuff.
Thank you. Another question regarding literature around usage of ML in experimental physics. So any books, papers, and in generally where these researches are published. So
well, yeah, great question. So as a matter of fact, right now that knowledge is collected in just in papers. But right now, finally, so we are preparing the textbook about applying machine learning to high energy physics. So it's going to well. We work on this about a year, so essentially since spring. So I hope it's going to be published next year. And this is really the comprehensive textbook on this topic.
Thank you. And the last question, isn't quantum computing the solution for such researches? Isn't current technologies weak?
Well, the quantum computing, I would put it in a different way. So quantum computing is a different approach to the computing. And of course, we know you know the principal feature of the quantum computing. So it does particular kind of problems pretty well, in contrast to the regular computing, which moderately solve the pretty arbitrary problem. So I believe that as soon as that the hardware, the quantum computing hardware get to some reasonable level that it could be used for practical calculations, there will be a boost of development algorithms for the quantum computing. And right now, from our perspective, actually we do not put much effort into this because it would be pure academic study. Suppose we find an algorithm to run quickly on the quantum computing, but we don't have quantum computer in hands. So why to waste time?
Thank you. Oh, and so new questions. Aren't we not? So how do we know if the current AE models are the most optimized to study the universe?
Oh, actually, I think I touched that point that it is not optimized at all. And so in the modern artificial intelligence is optimized to generate nice pictures of cats and to drive cars and make other industrial applications, which are pretty different from those tasks and problems which are required for the science. So it is not optimized at all. But we assume it. So and it is proved that artificial intelligence has a huge potential which we are going to use. I would put it something like that.
Thank you. And quantum computing is NP complete is the comment here. Are there any optimization combinatorial problems which, when solved, will help us better study the universe?
I think that is definitely yes, because the combinatorial optimization, if I understand question correctly, so the reconstruction, essentially the traces of the particles in the detector is that kind of the problem. So essentially, what what we read out, for what is the direct signal from the detector are particular points which we want to cluster, but actually those points are particular hits on the track of the particle, and we need to reconstruct the track. So somehow we have to clusterize those points, and it is a huge optimization problem with and this is one of the most time-consuming part of the reconstruction step in the data analysis.
Thank you. And the last question, aren't we not evolved enough to completely understand the physics of universe? The computer can actually simulate things better.
Again, repeat again, please.
Aren't we not evolved enough to completely understand the physics of universe? But computer can actually simulate things better.
I don't quite understand the problem. Do you understand?
Maybe you can, maybe can you please clarify your question? Okay, there is no comment, unfortunately, in time. I suggest that you can email us and maybe we can answer via email.
Yeah.
So
in principle,
once again, thank you for joining us. Yeah, so you can email us, please, and then we can review your question. And I would like to say thank you for joining us today, and further thank you for such a perfect lecture. In case if you have any questions, dear participants, you really can always email us. And I would like just to remind that if you are interested in our online Master of Data Science degree program, so tomorrow is the last date of applying. So if you are really interested, you can also, you have still a chance to apply. And so thank you once again. And
probably from my side. So we are interested in smart students who join the HSE, High School of Economics, and so they're participating in our efforts. So all that stuff. So if you are interested to be in touch, so that's the way.
Thank you. Yeah. Bye. Stay safe.